meter per second, and then let it do its thing, because then we're not gonna do every 5 minutes and notice, note the temperature. We don't have time for that, right? But we'll talk about the other experiment number 4. Okay? So that's experiment. Any question about this, or I think it's very straightforward.
Right. So for H experimental, that's what you got.
That's what you, yeah.
Your TH, your final temperature.
That's what the H experimental is this guy here.
Oh right. Okay. Yeah, calculate.
Yeah, the same as last week, except we'll have a different TS,
Exactly.
different TS value.
Yes,
configured.
Yeah.
yes. So don't use the ones from last week,
Right.
just use the data from
Yeah.
this week.
Okay.
Good.
Mm-hmm.
Now for number, so this is lab number 3. Okay, now we'll go on to lab number 4. Lab number 4 is a radiation experiment. And the title of the experiment is Verification of the Stefan-Boltzmann equation. Okay? So it says that Q, again, when you have a surface like this, you know that famous 2.5 inch by 2.5 inch surface, right? Which we're gonna heat up to a certain temperature, T sub S, right? And then we're gonna have that thermopile. So what it's going to do, it's going to radiate heat, right? Now the amount of heat that it radiates between that and the receiving surface in here of the thermopile is going to be, according to the equation, Q is equal to, maybe I should say, it's proportional to, that's what this symbol means, proportional to T1 over 100, maybe Ts to the power 4 minus T surrounding to the power, and you go like, what the heck is that T over 100 comes from? It's really, I could have just said T S to the power of 4 minus T surrounding to the power of 4. In the lab manual, they just divide it by that, because once you add 273, those temperatures become really huge,
Oh.
but it's really the same thing. Now, why am I not worried about A? Why am I not worried about epsilon? You think? Because I'm only going to be using one surface, one plate.
Like the black surface.
Let's say the black, I could use anything, since the black is already there, I'm
We're
just
not
gonna
doing
use
4
black.
different.
Yeah, we're not gonna do 4 different because it's pointless,
And then it'll.
Yeah, because we're gonna be comparing one to the other, right? So the A is going to be the same, epsilon is going to be the same, so forget about it, okay? So this is the idea then. It tells me that Q should be proportional to this. Now, how am I gonna approach, or how am I going to establish the proportion? First of all, there's a table in the back that tells you have variac setting. Variac setting meaning just how much voltage you're gonna put into the system, right? And then remember, this Q is read by what? Remember, we're putting in, connecting this to a voltmeter, right? And this voltmeter is gonna tell us the number of millivolts, right? The more heat, the more millivolts you're gonna get, right? So this reading out of that multimeter that we have there is essentially going to be the Q. Now, as we set the Q, I think the initial one was at 70, right? That's the highest one. And then we're gonna be reading the millivolts, okay, of the thermopile. We're going to read the fat, and then we're going to be reading what? T sub S, right? T sub S in degrees F. Remember when you use this equation, this temperature, is it in degrees F? Okay, it better be replaced by degrees Rankine, okay. Now, so you have Q, this is Q, right, essentially. Ts is known, and T surrounding is also known for each case. Because, you know, to figure out that they are proportional, you need to have at least 3-4 data points, right? So 70, then we're gonna be, after we get the data for this, then we're just gonna reduce the variac to 60. Then it's a big waiting game, okay? That's why I gave you the data for this one too, okay?
It has to cool down now.
Yeah, because it has to cool down. It does not cool down instantaneously, okay? Then you have to cool it down again, you know, to 50, 40. I don't know if the data, we did all of them or not.
Yeah, it goes all the way to 30.
To 30, okay, that's good, because we had time, I guess. Right? But the idea is the same, you know? It's just a setting, it's just a voltage that is less, and then you're just gonna wait for the stuff to go. Now, how do you prove if this is proportional to this? My suggestion, you don't have to take it, right, is to probably plot Q versus what? Well, Q versus this, right? Maybe TS over 100 to the power 4 minus T surrounding over 100 to the power 4. Now, if it is true that the this law is satisfied, what kind of curve should you be getting?
Be straight.
Straight line, it's proportional,
Oh, yeah, proportional. Yeah.
okay? So it's a better visual, in my opinion, to just draw those 4 points and then see if you can fit a straight line through that, or if it has that behavior.
So that's how we verify.
That's how you verify.
Okay.
What others can do, have done before, is to, for each one, we create a table in which they have Q here, T that, and then they look at how they compare and do the relative error. You know, that's another possibility too, if you don't want to plot it.
Right. There's an Excel table.
Yeah. It's a quick thing you can do. You could do both. Some people have done both before, though, just, you know, always the more you do, the better it is. It's analysis of data.
Okay.
So that's really the only extent of what chapter number 2 is going to be about. Lab number 4.
It's on the same bench, lab bench.
This one is going to be the convection, this one is going to be
Oh.
this radiation one.
But the same setup as last week.
The same, yes,
Yeah.
both of those
So
we're
our
gonna be,
pictures, we could use the same pictures.
you could use the same pictures if you want, yeah.
Okay.
The variac setting, that's just some arbitrary
Yeah, it's
setting
just-
on the dial
Yeah,
kind of thing?
it's a dial, really. It's a dial that kind of varies the power,
Okay.
you know? In fact, let's take a look at it before we come back and talk about the, can you bring the data?
Yeah.
Just for that. You see, this temperature now has reached, see, I think I told you earlier, 93 point something.
Yeah.
You know, now it's 95. This is not supposed to be exactly the same as last fall's data, obviously, because the initial temperature, I think, was higher, so you would expect to see a shift. But nonetheless, it's in the neighborhood of what we talked about last week, which is about 92, 93,
Yeah.
somewhere around there. So this is assuming this point has reached steady state. In fact, that's why I said to plot the curve and then to extrapolate, you know, just to kind of figure out where it ends. Let's suppose this is where it ends. So this corresponds to that 0 meters per second. That's free convection, okay? I replaced the batteries. That's why I came over here too, make sure that tested all the batteries. Turns out that one of them was bad. It the other ones were good, so I replaced that one. So this one is actually working, okay? This is called a, what is it called? A hot wire anemometer, okay? It's a very interesting piece of stuff that is used a lot in fluid. It's just a little, very thin wire that's been calibrated such that depending on how fast the fluid is actually coming through and what is the voltage change, you know, it tells you what is the fluid velocity, okay? So this one turns out that you can actually read either the temperature or the velocity. See, it's got two curves.
Mhm.
One of them is red, and if I have my glasses, but that's okay. Meters per second, I think, is at the top. And so the red curve reads the velocity, the blue curve reads the temperature, okay? Obviously, we're gonna be interested in the, you're gonna be interested in the red curve, right? Probably be a good idea to take a picture of that, just the front screen
The
of
red
that.
curve is velocity.
Yeah, I think it should be written there too.
And then-
It should mention
I'll double check.
meters per second and
Curve.
Fahrenheit.
Thanks.
Okay,
Yeah, okay.
so what I'm going to do now is I want to simulate a 1 meter per second flow over the plate, okay? So this is the stuff that we have not used last week. So what you need to do here is to turn on the fan. First of all, before I do that, turn this guy up to velocity because I'm not gonna measure the temperature. So just click it up,
Oh, cool, okay.
velocity, and then start turning. And then usually what you do is you kind of just
Tap it.
tap it, you know, that's for temperature, sorry. You go like this, you see it's kind of zeroed, right?
Yeah.
It's right at the 0. You come back here, if you hit it like this, it moves, then you have to kind of roll it, zero it using this guy, okay? But I already did it earlier, so. Now, what thing you need to do now is to turn on the fan.
And that's our, oh no, the anemometer was, not the anemometer, the variac setting, that's for
The
level.
variac is for that guy,
Okay.
okay? So this one, I'll just turn on the fan. You see, this guy is kind of coming in like this. Now, big mistake that a lot of people, even experienced guys in fluid mechanics make is, see, the orientation of this guy. See here? The hot wire is kind of right there. So if it's, since the fluid is coming in like this guy is better. But how the heck do you know that it is in that orientation? Okay? Just like the pitot tube, right? Remember?
Yeah.
You kind of turn it back and forth until you reach the peak value. That means you are really,
It doesn't click in a certain way. You
well, it
can
does not really click. It's just, you see
set
here?
it right in there.
Now visually, this is probably gonna be okay.
Right.
You know, coming in like that. But at the same, I mean, you can also do it with this guy. But what I like to do, as I get it to a certain velocity, you know, before I select it, I just kind of go, see? So if you go, this is probably the highest. Well, that's if you want to play with it, you know, just make sure that you're getting really the peak value. It's okay to go beyond, see, now it's going down, okay? So it means it's wrong orientation.
Right.
And then you want to capture the moment when it's kind of at the peak.
I feel like it's higher.
Whoop. All right. So let me just make sure. Yeah, that's good. That's good. Now, obviously we don't have 1 meter per second. Now, because the orientation is fine, just turn the knob until you get to 1 meter per second.
Sounds like it's moving slow.
Okay, so that's
It's gonna
probably-
take off.
That's probably gonna be good enough. you know? So what you're gonna be seeing now is a temperature that's gonna be,
Decrease.
now it's a waiting game again,
Right.
which we don't wanna do,
Yeah.
okay? So while it's doing its thing, right, let's talk about this guy, unless you have questions about it.
I don't think so.
Okay. Now coming back to this one, I already, set it up. This is against this, right? And that's a black surface. It's 9.68. It looks pretty darn good, I'm sure it's because this one does not take as long as that one to converge. So in fact 968, it's still 968, 967. It's not truly changing, right? Aside from that just little fluctuation, that's not a really problem. This is the Variac that I was talking about. Okay? So it's written Variac. It's already set at 70 right here. Okay? So that's our first data point. If we were to do this lab in class, right? That's our first data point. It reads 9.67, right? And now, if we were to be doing this in class in a normal fashion, the only thing we'll be doing is we'll chase the second data point. The second data point, if you would want to turn that thing down to 60, the Variac, let's just see what happens. Obviously, you would expect that 9.66 to go down, right?
Right.
Okay? It's not going to happen instantly, obviously. Instantaneously, I should say. You see,
Slowly going, yeah.
it's already coming
Yeah.
down, right? What I meant to say, it's not going to reach steady state immediately. It's going to take a little time. So we're going to wait for that, right? So both of these things are doing their own stuff. So while they are doing so,
Is there a heat?
oh yeah,
Oh, yeah.
oh yeah. You see, now you just blunt it. You see?
Right. So it comes like. Okay.
Okay?
Yeah.
All right, so, now let me shift to something else. By the way, something I should have done also, because in one of the forms, you're supposed,
Oh, yeah,
it
yeah.
says, have you talked about, it says during class you will receive a reminder about health protocols, obviously. We have to mention something like this in order just to check the boxes. The 6-foot stuff, just to make sure that we are there, the cleaning of the hands and all that kind of stuff. And this was sent to me this morning, just about masks. Obviously, it's nothing that we don't really know.
I need a picture of the board,
Mhm. So, this is just talking about the mask. They should cover the bridge of the nose, be snuggle with the chin. What is it? Oops. Obviously, it has to be something that fits. And then there's an interesting thing on how to handle masks. I'm sure you've probably heard about this. My wife keeps reminding me about this all the time. Don't touch the mask if you wear. Handle it from this.
That's why these masks make me touch my face more.
Exactly. And
Oh,
it's not
like,
like, I
ah,
try to adjust and go, no,
drives
you
me
messed up
nuts.
the whole thing. You touch
Yeah.
your phone, you touch your, and I go like, God, I wish I didn't leave.
Yeah.
So, again, it's one of those things, don't touch the mask while it's on, when adjusting the mask, clean your hands first, and then don't take it off. To make a phone call or touch the phone, but you see? All right, keep clean disposable masks versus cloth masks. Distancing, that's really the main thing in my opinion, as long as people don't really just get too close to each other, and you have things, the mask, I think things should be hopefully fine. Okay, so that checks up the box. So the topic of the project, I think, concerns the heat exchangers, right? So what I did in here, obviously you have the lecture, the full lecture in MEC 323. And you,
I think when I looked today, maybe I'm wrong.
on Canvas,
The Mac 323, yeah, it got taken down. I don't have access to it anymore.
oh,
Is there a way? I mean, I was trying to save some of those PowerPoints.
what do you need from MEC 323?
Well, you said this is in 320. Oh no, this
No,
is
no,
in
I can post this, that's no
Okay,
problem.
yeah.
In fact, I can post the entire chapter if need be, you know, this is a truncated one, you know?
Okay.
So this is what I was planning to kind of post on the thing, you know, for, figured that you still have the book.
I do.
But if you need the original chapter, just let me know. It's not a big deal.
Yeah, I have the book.
So the chapter, just before I talk about the project itself, because it really talks about either parallel or counterflow heat exchanger. So I'm just going to just give you a couple of reminders about those. Couple of reminders. So on heat exchangers, obviously, these are just some hardware, if you will, that anytime you talk about heat exchanger, you're talking about two fluids, two different fluids that are not mixed, and they are separated usually by a solid surface. It's kind of in a simplistic way, that's really what it is, okay? So the two easy ones or the two clean ones that we deal with are either the concentric tube heat exchangers because they are easily analyzed. This one is a parallel flow heat exchanger. This one is a counterflow just because they flow in opposite direction or in the same direction. But for both of them, obviously, they are parallel, okay? There are other heat exchangers such as the cross-flow heat exchangers. This is when the two fluids are not in parallel directions, but they are in perpendicular directions. And then you also have a shell and tube heat exchangers, which I'm not going to be doing in here. And then, and this is a pictorial of that, and obviously there is also a compact heat exchangers when the space is really small and you really need to extract a lot of heat, then you rely on compact heat exchangers. In terms of analysis, so really what you have when you talk about heat exchangers, you typically have a hot fluid on one side, right? Cold fluid on another side. And this is a solid surface. Okay? And because this is a hot fluid, this is a cold fluid, typically the heat always goes from hot to cold, right? The number of resistances the fluid will encounter as it goes from hot to cold is going to be a total of 5. Why? Because if you guys remember from MEC 323, we always said that you typically have what? You have some fouling on this side. You're going to have some fouling on that side, right? And then you're going to have usually have convection resistance, right? Then you're going to have fouling. Then you have conduction resistance, right? Then you're going to have fouling. And then you're going to have another convection resistance, right? 5 things to go through, right? So convection, fouling, conduction, fouling, and convection. So total number of 5 resistances. And usually for the heat transfer, we typically write it as Q is equal to UA delta T, okay? Okay. This is the equation that usually tells you about what is the heat transfer for a for a heat exchanger, and when we took that first class, I explained that we were trying to, out of the three equations, namely convection, conduction, and radiation, convection is the easiest one, you know, does not have powers, it does not have derivatives in them, right? So that's why the heat transfer for heat exchangers is mimicking really the convection heat transfer coefficient. So the big question here is usually A, the area that is common between the solid and the hot and the cold wall, the hot and the cold fluid, I should say, the area is pretty much known, okay? So the big problem then becomes, how do you calculate U and how do you calculate delta T? Okay? Two different things. So to find U, these are the 5 resistances that I talked about. Remember, 1 over HA represents the convective resistance. This is the fouling resistance. This is the conductive resistance. This is the other fouling resistance, and then this is the other convective resistance. In most cases, the fouling is usually ignored. And also the thickness of the wall of a pipe is usually neglected. So in most cases, the only things that are typically considered, the only 2 resistances are the convective resistance on the outside for the hot fluid, if the fluid is flowing on the outside, and the convective resistance on the inside, okay? So a problem of heat exchanger really reduces to analyzing again, how do you determine H is by looking if the fluid is laminar, if the fluid is turbulent, and then choose the appropriate Nusselt number, or in fact it's this part right here still applies, for heat exchangers, whether you're doing the HI or the H out.
So it's the same stuff.
Yeah. So it's that stuff back there. So overall heat transfer coefficient, and then in terms of, so that's to figure out really what your A is, okay? Now, to find what delta T is, if you remember, we looked at the energy balance, because the temperature or the heat that is lost by the hot fluid is exactly equal to the heat that is captured by the cold fluid, okay? Why? Because, we're assuming that the outside is all insulated and we don't have any other losses.
Can you go back 2 slides just really fast? One more.
One more, okay?
Okay, no, I'm good, thank you.
Okay. Now, by doing so, remember 2 equations that are always used when you're doing heat exchanger is this equations right here. Remember, what I said is that you typically need 4 temperatures, but when you have only 2 temperatures, when you have only 3 temperatures, and you want to calculate the 4th temperature, you just do an energy balance, right? So these 2 equations, right? Because this has to equal to that, by equating these 2, you will always try to find an unknown temperature. Now, the other situation is, what delta T are we going to use? Well, the delta T, see that equation right there at the bottom is the equation for the heat transfer for a heat exchanger. But the delta T it's a bit of a headache, because if it's a parallel flow heat exchanger, that my temperatures are doing this. But if it is counterflow, my temperature is doing what? Is doing this, right? So this is at the section 1, this is at section 2, this is at section 1, and this is at section 2. This is for parallel flow. This is for counter flow. Okay? So between the entrance and the exit, you see, for parallel flow, the temperature difference is really high at the entrance, right? And it gets smaller and smaller as you go towards the outside. Whereas for parallel flow, for counterflow, it's kind of even throughout the entire thing, right? And remember what we said in MEC 323 is that the counterflow is better, more efficient than then parallel flow, given everything is the same. Now, again, you guys remember this slide we talked about? This is for parallel flow heat exchanger. You see how the temperature changes from the inlet to the outlet. So when you are using this equation, the delta T is calculated using what we call the logarithmic temperature, log mean temperature difference, right? And the log mean temperature difference is simply delta T1 minus delta T2 divided by the log of delta T1 over delta T2. End of story, okay? That's if you are using parallel flow, but if you were to do counterflow, of course I don't have the picture for counterflow, but it will be the same, okay? Except that for counterflow, this temperature would start from here and go all the way there, right? But the equation is identical. Now, we talked about this when you have 3 temperatures at least that are given. Because to calculate delta TLM, you clearly need 4 temperatures. So 4 temperatures are given, we're great, right? If 3 temperatures are given, I can get the 4th one using the energy balance, right? The 2 equations that we talked about before. But what if it's only 2 equations, 2 temperatures that are given? Then this method is obviously not going to be useful for me. And then we talked about using what we call the effectiveness and NTU method, right? And I'm not gonna go through this one unless you guys wanna do it. That involves the Qmax and then the Cmin, right? Defining the effectiveness of a heat exchanger. To define the effectiveness, you must define, for example, what is the maximum possible heat transfer that you could always have. And the maximum temperature is going to be, the maximum Q will correspond to the one that has the lowest C, because remember Q is equal to C delta T. The highest delta T corresponds always to the minimum C, okay? And the maximum temperature difference is really the inlet temperatures. You know, if I have hot fluid coming in at 200 degrees, cold fluid that's coming at 20. So I could say without looking at anything that the greatest possible temperature difference I could ever get is just the temperature difference between the 2. So why are we calculating this? We were just calculating it just to kind of, just like the Carnot cycle, we have to have something to compare to, okay? So if I know the actual Q for the heat exchanger and I compare it to Qmax, at least it's going to tell me how effective my heat exchanger is going to be. So knowing what Qmax is, so you define then the effectiveness as simply the actual Q that you have in your problem, in your heat exchanger, divided by the Qmax. Obviously, the higher the value of epsilon, the better the stuff is going to be. If epsilon, THI, and TCI are known, the actual heat transfer rate then becomes Q is equal to epsilon Qmax, but I know that Qmax is Cmin divided by that. Now look at this equation. If I can figure out really what is the Q associated with the heat exchanger by knowing what? By knowing just the 2 temperatures, THI, TCI. I don't need to know TC out, I don't need to know T hot out. But again, what I need to know is what is this epsilon? So where do we get this epsilon from? Remember the charts or the equations, right? For any heat exchanger, that epsilon, that effectiveness is actually a function of the ratio of the C's, because you have 2 fluids, so you will have 2 values of C. And then this NTU, where NTU is actually UA divided by Cmin, okay? Now, that's, I think, all there is to be said about this one. If you know to calculate the effectiveness, you could use either equations, you know, in which you know CR being Cmin over Cmax, right? And then if you know the NTU, then you can calculate epsilon, and then from there you can calculate the heat transfer, right? Or you could calculate the NTU if you know what the effectiveness is. So it's either way. And to finish my last thing in here, these are some equations But you could also use some charts, you know, some people prefer charts is better. You know, it's because those values are not really exact, so you can actually just look at, it's about 0.22, 0.24, it's good enough. And then read from there. So you could actually read the value of the effectiveness depending on what type of heat exchanger you have. Like on the bottom left, you have parallel flow, counterflow on the right-hand side. You could have maybe shell and tube, you know, and a whole bunch of other things. And last but not least, we talked about two types of analyses when you talk about a heat exchanger. That's how we finished the chapter 11 in heat transfer. We said that you could either be analyzing a heat exchanger or designing a heat exchanger. Okay. Analyzing, which is called the performance analysis, is when you are given actually a heat exchanger, and then you are doing an analysis to see if there is a process or a heat exchanger thing that you want to achieve. Can that thing that you were supplied with do it? So you're not analyzing, you're not designing in that case, you're just analyzing. As opposed to designing, which is what your project is all about, you're supposed to tell me, for example, how big what the diameter of the thing is, how long the pipe is going to be. Anytime you're sizing a cross section or the length of the pipe or something like that, that enters in the domain of design. Okay? So, and that's really what this thing is all about. So we just talked about the design versus the performance versus design. Anytime you do performance calculation, usually the NTU is given, but anytime you're doing a design, it's most likely that you're going to be looking for what is the value of the NTU, because in the NTU there is an area. An area will include the diameter. That's the last slide about this.
So we need to give you an area and a length for our
Yeah, it's
design?
like what kind of pipe, you know, how big the pipe is going to be, and how long is the pipe going to be needing, you know.
Okay.
And that's, hopefully I have the thing in here. I think all I gave you is this. Remember, this is not a, this is a one-page thing, right?
Right.
And it says this. It says that you have benzene is used to manufacture, for the manufacture of detergent, okay? You're asked to size a double pipe heat exchanger to exchange heat between the benzene and water, okay? The benzene flow rate is given to you as 4,500 kilograms per hour, and it's supposed to be heated by from 24 degrees to 38 degrees. That's, you know, because your manufacturing stuff dictates that, okay? Now, how the heck are you gonna heat the benzene, okay? Well, it turns out that you have water available at 60 degrees. That's the only thing you're told. You have water that is available at 60. So, your job is to select an appropriate heat exchanger, and I'm suggesting maybe parallel or counterflow, either one you want to do, and determine the required water flow rate. Okay, at what rate are you going to get the water into the thing from? Now there are some constraints, and I'll tell you about those just to kind of give you time between now and next week to kind of think about them. First of all, I'm giving you some properties. You know, some students actually go to the lab online and get properties if they need them, right? I don't really care as long as it's kind of similar to, you show the source, okay?
Or we could use it.
Or you can use it, yeah. Now, let me tell you something about what the restrictions are that we typically don't deal with when you're just taking a class in a normal fashion. Right? Now, pipes that carry a fluid, obviously if you have a double pipe heat exchanger, obviously you're going to have one fluid that's flowing in inner pipe, right? And the other one in the jacket, right? So both of them are essentially internal flows. right? And the heat transfer will be proportional to the H because it's convection. The heat gets removed by convection, as we talked about here. Now, to get the maximum value of H, to get the high heat transfer, do you want the fluid velocity to be slow or do you want it to be high in general?
We're trying to heat it up.
No, when you want to have heat exchange by convection. Slow, but you want it to be really slow. You think a lot of heat is going to come out if it's free flowing slowly? Remember, let's think flow over flat plate. Do you have better heat coming out of the plate if the flow is really fast on top of the plate, or is it really slow?
Fast.
What's that?
Faster is.
Obviously, it's faster, yeah. I mean, convection is always better when the fluid velocity is fast, right? If I have a hot cup of coffee, I better blow on it really fast if I want to cool it faster, right? So, but in order to create a fast, when you have, let's say you're talking about a pipe, right? So we agreed, hopefully, that you need to probably have a high value H, right?
Mm-hmm.
Which is a high. Now, what comes along with having fast or high velocities in pipe? What's the downside of that, you think?
Turbulence?
Is that?
Turbulence?
Yeah, turbulent is one thing, but what comes up with turbulence though?
What comes up with turbulence?
Well, remember the Moody charts, right? As the Reynolds number goes up, right? The values of F tend to change, right? So you have high friction because you have, remember Darcy's law, FL over D times V squared over 2G, right? That's the head loss, if you will, right? And the head loss is proportional to the velocity squared. So on one hand, you're creating that high velocity, on the other hand, you're creating the losses. So to keep a fluid moving through a series of pipes like that, you need to really make up for the loss in pressure. So that's another big headache, okay? So that's why in real life out there, there's a lot of piping engineers, engineers who just do pipe flow, right? And those are the guys who actually do the analysis to go like, I don't want the flow to be really slow so that it doesn't do anything, right? I don't want it to be so high so that it creates other problems for me, right? So I have to have some values in between. So based upon their findings, okay, I'm just giving you the notes and the additional notes. It says for your pipe carrying the benzene or the water, because I don't know which one you're going to choose. Are you going to choose the benzene to flow on the inner pipe or the outside? I've seen it done both ways. You just need to justify why are you choosing, there's no right or wrong, but why did you choose, for example, benzene to go inside or outside or water to go inside or outside? Just think about that. Now, for your pipe carrying benzene or water, assume that the maximum fluid is in the range of 1.2 to 3. Okay? So I don't want to see a flow on either one of those pipes, outside that range. Okay? So always try to kind of go, maybe I should start somewhere in between. So I've seen some people kind of go to the edge and then they find themselves on the outside of the thing. So play it smart. And another way, if you want to do this one in the least amount of time, use Excel.
Yeah.
Use Excel because, you don't want to change a number and go like redo the calculations by hand. That would be, you'd be torturing yourself, right? If you put in all the variables there, right? Because this is an iterative process. Every design process is an iterative process, right? Not two people are going to get exactly the same stuff, but it's you're repeating the calculations and you wanna make sure that you're not outside the bounds of what you're supposed to be doing. And sometimes you may say, maybe I should reduce the length. What if I increase my flow rate, for example? Okay, what does it do? But you know that the flow rates affect what? They affect the velocity in the pipe, et cetera, et cetera. So, as long as you want to make sure that the maximum fluid velocity is in the range of between 1 and 2 and 3, make sure you specify whether you're using parallel or counterflow. Obviously, that goes without saying, right? For flow in the annulus, because obviously you're going to have flow inside a pipe, and then the other one will be in the annulus, and if you guys remember, that's in chapter 8, right? If the flow is turbulent, you can use the Nusselt number correlation for regular turbulent pipe flow, such as the Dieters-Boteler equation. And remember, anytime you have flow in the annulus, you can actually use the equations for flow in the pipe as long as the diameter is the hydraulic diameter, DH, because, you know, let's say it's at the annulus, what kind of pipe, what kind of diameter are you going to be using? Inner diameter, outer diameter? Remember, anytime you have something like that, you have to use the hydraulic diameter. So look at chapter 8 for the definition of the hydraulic diameter. And make sure you also indicate whether which fluid is flowing where and why you made that type of decision, okay? So it's, you know, don't think of it as a very complex problem. It's just either if you're using parallel flow, it's just kind of a more general parallel flow problem calculation, except that you're not given everything, you're designing, so you're, and by the way, when you calculate diameters also, it has to be some known diameter stuff that's out there. So you're not gonna, if you find like 2.32 centimeters or something like that, you know, is that something you can just go and buy, you know? Or is that something that's going to be, or is that something that's going to be different, you know? So that's the situation.
Can we
So-
have to say, the length as well?
Obviously, you need to have a
Yeah, you
length,
need a
because
length.
because why is the length important? Why?
Well, for, yeah.
Because it's the area between the hot fluid and the cold fluid, right?
Mm-hmm.
The heat transfer is going through what? Through the pipe,
Mm-hmm.
right? So that area is equal to what? It's equal to the diameter, the perimeter,
Mm-hmm.
which is a function of the diameter times the length.
But there's no like stipulation on how long it needs to be?
Well, there's no, yeah, so of course you want it to be, you don't want it to be huge,
Right.
you don't want it to be reasonable, right?
Well, isn't that like relative? Like, what is it?
It's all relative, but again, if you will find that it's not that, the difference is not gonna be that huge, okay?
Okay.
But you don't want, you know, I had one student one time said it's 0.1 meters. Really, you know?
Yeah, no,
Of course, when you find something like that, that means you made, just like I told them, it's probably a property error, 10 to the minus 3 somewhere that you lost, right? So, you know, it's like 10 meters or something like that, something reasonable, I think, kind of makes a lot of sense.
It should be 10 meters long?
No,
Oh,
but remember, this is a pipe like this, that does not mean it's just straight like this, you don't have to do this,
oh,
You know.
okay.
Okay.
Did any of our homework problems have a size pipe before, or is this the first time we're really kind of?
Size
Did
would
they
be.
size the diameter?
Sizing? Oh, yeah, we had
Mhm.
find length, we did many of those.
We did?
problems
Okay.
before,
Length?
Yeah.
I thought it was just like diameter.
Oh, we
I
did
don't
lengths.
remember.
Oh, yeah.
They're all looking.
We did lengths, particularly the last problems, you know, there is, anytime there is design, it was finding what the length is, and finding that through UA, essentially.
Okay.
So, it's given to you the third week, so you have time to start, you know, yes, as you can next week or something like that. If you have any question, just give it a good shot, you know, just try to be methodical and try to create your Excel, you know, see if there is one iteration of calculation that is done. Make sure you put all that stuff in there. That way, if you just change one in the variable, hey, you know exactly what's gonna come out of it. You know, don't torture yourself. Because you're never gonna get the thing just in one shot. Good. And that's pretty much, okay, so we talked about lab 3, lab 4. We looked at what we did in the lab back there. We did the review on heat exchanger, and we just defined what the project is all about. Now let's just take a look, unless there is a question about this.
No, but can you post those chapters? Or your condensed version, 11 and 8?
The PowerPoint?
Yeah.
Oh, okay, yeah,
Yeah.
I would,
I have the book, but the PowerPoints are nice.
8,